this lab for next week. It's a lot of fun working with this one. So I'm adding a little bit more to it. This is so boring. I think I developed this 2 years ago. I keep using this for twice already. We'll go through the timing. So you know the setup time, hold time, which are super important concepts in digital design. So it's a really good experiment for FPGAs, I think, because you guys are actually remember how you used it. If you use it in Arduino's, right? It's gonna be just one line in C. It'll be LCD parentheses. Then you just throw the whatever the text you want to display over there. So the software will do the job for you. But for here, we have to code up the driver. The driver is a digital module directly communicates with the digital pins of the LCD module. So I have to understand the logic first, the logic and timing. Even though this is a very old LCD display module, but still being used in a lot of places. You can buy some toys from different places, scientific instruments. They want to reduce the cost of it, so they like to use this 16x2 LCD modules. It's really classic LCD module. It's everywhere. And you can add another line, right, on resume saying you understand the timing of the LCD display. And because this is so fundamental, I think this applies to other display modules. It could be the OLEDs and all other types of displays. They probably use the same or a similar concept, to control the display. Right? So let's take a look at this one and see if we can, if we know the overall goal of this experiment. Alright, so the wireless connection, it will be really beneficial that since I'm recording this lecture, so you guys take a look at the circuit. I'll just place it under the camera. This could be very confusing. Sometimes these are your choices, right? You can use the power supply from the 3.3 volts from the FPGA, or you can use it from the power supply. It probably doesn't matter for that one, but for other options, if you don't know how to do it, you're stuck there forever. So first, this guy requires a 5 volts power supply, right? And we all know that the FPGA board is a 3.3 volts, so it doesn't have that 5 volts to support it. That is why you have to use this Arduino Allegro power module. I don't know if you have used it before. This is a very common DC power module, and this one has two terminals at the outputs. You can see this is plus minus, right? Plus minus. And here as well, plus minus, right? So in that case, if are given with the breadboard, you would like to plug in this one on this side instead of the other side, because you plug it in this side, the plus is over here on the left-hand side, so it's aligned with the right rail, which is the power rail. So plus goes to the right rail. If you plug in this module to the other side of the breadboard, it will go the opposite way. So the plus goes to the ground. So it can confuse people a lot. Right? This is a little tip here. You're getting that, right? It's pretty simple. You plug in this way, make sure plus is aligned with the red rail, and the minus is aligned with the black rail. So which is ground, right? Same for the other side. Couldn't see it very clearly, but you can probably tell it's a plus minus as well. And we all know that the breadboards, the two sides, the rails are not shorted together, so the power rail and ground rails are not shorted. However, since you have a PCB, when you design the PCB, remember you have a common ground, right? So the PCB actually has a common ground. So if you have these two minus terminals both plug into the two rails separately, but the thing is the PCB has a common ground, so it's actually shorting the two minus or the two grounds together, so you are getting a common ground. And you have different options. This is a little header pin. You can switch it in between 5 volts output or 3.3 volts output. It's just a very simple header. You can unplug it and plug into the other option. It shows you that on the back, you can see it's either 3.3 volts or 5 volts VCC, right? So the 3.3 volts is 5 volts. So by doing that, you can have a common ground for the entire breadboard, for the two ground rails. At the same time, you can pick up 5 volts for one side and 3.3 volts for the other side. Does that make sense? So the key point here is that since we know when we design any digital system, the first point is the power supply, right? So we definitely know that there's no like wireless modules. There's no motor, right? Motors usually consume a lot of power. It's a low impedance stuff, heavy load. We don't have it. It's basically just a digital, right? Digital oscillations from the FPGA, and then the most power consuming part is probably the backlight of the LCD. It's the LED, pretty bright. It's probably consuming the most power. However, we don't expect everything will go beyond 1 amp. This could be an experience, right? So when you are dealing with something like this, you have multiple sensors, microcontrollers, FPGAs, the display modules. It's gonna be under 1 amp power rating, if you want to put it that way. So the power rating will be lower than 1 amp. So in that case, you grab a little. So this guy has these two power regulators. If you see a power regulator like this, it's probably AM1117. When you design the PCB, you should know this really well. Okay, this is really popular and low cost, probably just several cents, right? If you purchase it from some of the Chinese vendors, they can build it just within several cents, super cheap. Yeah, so this is a really popular 1 amp or a little bit lower than 1 amp power regulator. And if you just have all those digital components, this is probably one of the best options you can have, right? This is 1 amp. And you can see those is Aligu. The name of the company is called Aligu, right? So the Aligu microcontroller, you can see Aligu microcontrollers. So they also manufactured or designed these power modules as well. So they use 5 volts regulators, 3.3 volts regulator. So this is you can see it's a 6.5 to 9 volts range as the input, and you can pick up one of the adapters like this. So you're looking at the voltage output, right? Let me see if you can see it. I'll let you guys tell me what the voltage output it is from this adapter. Could you read it? No, it's not designed for that purpose. So it's a 9 volts DC output and 650 milliamps. Okay, even that is still enough. I mean, we're actually not expecting more than 200 milliamps, even though what I'm saying 1 amp is you'll never exceed 1 amp. So, but the very common power consumption is usually under 200 milliamps. For the digital system like this, I can just do a very quick estimate. Okay, just keep that in mind. So for this adapter, it's a 650 milliamps. It's more than enough. And this is 9 volts output, so I can definitely use this guy. At the voltage input for the voltage regulator, here is taking in 6.5 volts to 9 volts. All right, so this will be regulated to 5 volts by the first regulator, and the first regulator outputs 5 volts, and that is being used as the input for the second level voltage regulator, which is a 3.3 volts regulator. So stabilize the voltage to 3.3 volts. So this is how this is designed, right? From 9 volts to 5 volts, and then step down to 3.3 volts. And these are called buck converters, and they are going down. This is step down for each time. These are not boosting the voltage. You can also buy boost converters. They can boost the voltage to a higher voltage, but usually we don't do that. These are usually more expensive. They have to use inductors and all these kind of feedback circuits. So these are very cheap and low and convenient, a small footprint. So you can purchase them. I think if the whole module, the entire module, including all these USB headers and everything you buy from China, is probably lower. It's going to be lower than $1, $1 US. You can imagine how cheap they are. I mean everything, including the PCB and everything, lower than $1. So this will be good enough for us, right, for our application. So now we figure out the power supply, and even though you'll see on the FPGA board, you see here, it's a 3.3 volts output, right? 3.3 volts output, and ground is on. So the first one is 3.3 volts, and the second one is ground. So here's a more clear picture here. See, that's the layout of the header pins. Yeah. So here's the IPGA chip. At the bottom, it has a lot of pins, right? You couldn't see it. They don't have the pins just surrounding at the edge of the chip because you don't have that much room. But however, you have a lot of room underneath it. So that's why they have all the little balls or pins directly underneath it, and you can fit a lot of pins over there. You can see the pins are shorted to 7-segment displays, shorted to the buttons, shorted to the switches and LEDs. You couldn't see it because there are traces on the PCB, right? But also they also have GPLs, which are general purpose Ls, right? Just digital Ls. These Ls are being shorted to the header pins over here, so make them available for the user. If you want to connect anything to it, you can easily program the FPGA and the interface to communicate with the modules. We call it peripherals, right? So you can always communicate or interface with the peripherals. Whatever, it could be light sensors, could be microcontrollers, digital ports, could be actuators, motors, whatever. Okay, based on the design, you can customize pretty much everything with it. So these are the GPLs. You can see the layout. This is a 2x8, right? 2x8 array of pins. So the layout here is the same as the layout over here. So in that case, if you flip it, you can see this is being bent, and the headers are on the side. So the top row, if you look from the side, there's a top row 8 pins and bottom row 8 pins, right? So the top rows are shorted to which side of the column here?
The right side.
The right side, right? The top rows are here and shorted to the right, and the bottom rows are shorted to the left. Does that make sense? So when you're mapping the pins, mapping the holes to the pins, you know which is which. And one thing is super confusing for the IPGA. I think the designer probably don't have a second option over here because they have to fit the power and ground in here. So you can see JA1 being labeled on the board is actually not JA1 of the in the constraint file. See, constraint file defines all the ports. Let's see, where is it? I just saw it. Oh, here, right here. So in the constraint file, you have JA ports, the JA0 to JA7, right? You have 8 ports of JAs. It's probably more, maybe up to 15, I forgot. But let's say we're only using the JA0 to JA7. There are 8 ports, right? 8 ports from 0 to 7. However, you don't see JA0 here at all, right? You see the labels? And the red labels are for me. I just labeled it just for you guys. But you can see they don't even have JA0s. So these JA1, JA2, JA6 to JA12, these are JA schematic ports. These are used for the schematics, not the layout, or not the physical ports of the chip. We just need to know it. We don't have to know why they did it that way. It's probably easier for them to label the schematics, the pins on the schematic. But let's disregard that one, because the JA1 here, you can see from the constraint file, right? The JA1 is not going to be the JA1 over here. That means if you, in your IPGA from the top level, if you make a connection, or from the top, you need to declare ports, right? So if you declare ports of JA from 0 to 7, and the JA1 of it wouldn't be the physical JA1 here from the label here, because this is a schematic label. Does that make sense? It's just simply not that port. Okay? So JA0 here, if you declare it, you are trying to short something to JA0, okay? and it's gonna show up here. JA0 will be here. JA1 will be the second one. Will be JA2. So you don't look at these labels. We can totally not even look at it, but we have to look at the ground power because these are definitely power and ground. But for the JAs, if you want to map the JAs from the constraint file to the JAs on the board, you need to look at the ones I labeled on the right-hand side and the left-hand side over here on the other side. Does that make sense? So the JA0, JA1, JA2, JA3, so on and so forth. Any questions on this? You can just disregard these ones. So another thing to let you guys know, just a very quick tip here. How did I figure that out? Okay, because these, you can see pin J1, L2, J2, this is from the constraint file. So these are the real physical names of the pins of the chip. Okay, you can see J1 is actually JA0. So where's J1? It's here. Which is schematic, from the schematics, it's actually JA1. So that's how I know it, right? So J1, I'm looking at J1, which is the real physical name of the pin of the chip. Is that shorted to JA0? So that's the physical pin of the chip, and the name of the pin is actually called JA0 from the constraint file. That's what I want to use if I want to connect something to this physical pin. It's the same concept applies to other pins. Let me give you an example. What about H1? H1, if I want to use H1, what name I actually use in my Verilog?
JA4.
Yeah, it's over here. Okay. And also we are using JBs as well, just 2 ports, JB0 and JB2, it's the same stuff. JB0 is not JB1, but it's at JB1. Or it's a physical pin called A14 of the physical chip. It's over here. All right. If you look at the header, it's actually on the top right corner of the board. And so JA4 or JB0, if you look from the side, and looking at it, would that be the top one of the pins on the top row or bottom row? JB0. Top row, right? Here is shortest to the top row, and the inner ones are shortest to the bottom row. Does that make sense? Okay. And usually, if you look at the FPGA, so when you connect your FPGA to your computer, definitely it's a digital device. It requires power, right? You have a separate power cord. There's no separate power cord. There's just one single PC, one single USB, right? So USB is shortest to the laptop, so it sources power from the laptop through the USB. And what's the standard voltage for the USB? USB is a standard port. Should be 5 volts. Keep in mind, USB is 5 volts. USB is 5 volts forever. Okay, the 5 volts is power supply to the FPGA, and that 5 volts goes to some of the regulators on the board and being stabilized to 3.3 volts as a digital logic for the whole thing, right? So that's digital logic. That's why you are getting a 3.3 volts available at the header pin over here. So can we just directly use the 3.3 volts and 5 volts available on the FPGA to power up everything, so we don't have to use this separate power supply, right? Like this. Could we? Is that a good practice? Why?
Because you don't want to be sourcing a lot of current from it.
Yes, right. Exactly. And we don't even know what's the current rating of the laptop is, right? Or what the current rating of the traces on the FPGAs. They probably could be very thin traces, and they're not rated for example, more than 100 milliamps. But your peripherals overall is about 200 milliamps. It's gonna heat up the traces on this board. You just don't even know, because this guy is just used for digital logic, not for power, right? You probably, this is a better practice, right? Since you know this is exactly 650 milliamps, right? You are confident it's gonna power up everything, right? And the connections, I already listed. So in the past few years, I never did that. Students were able to figure it out. It could be a little bit confusion, okay, and a little debugging during the lab. So make my life easier. So I just listed all the ports. J0 to 7 is shorted to D0 to D7. So D0 to D7, these are just the 8-bit data ports of the LCD. Okay, 8-bit data ports, very simple. There are not too many ports, right? So 8 bits, so the 8 ports are already done. So they are shorted to J0 to J7. Where are J0 to J7? It's over here, right? J0 to J7. Just by looking at this pinout, you can easily connect these ports to your FPGA. Just simply do a connection, make the connections. And remember, I just told you guys, right? So the LCD parts of the LCD's VCC should be powered up by what? How many volts? 5 volts. And your FPGA is a 3.0 volts device. You're like, whoops. Can I burn my FPGA just by directly connecting them together? Why or why not? Oh, you got a 5 volts device, right? Sounds like pretty dangerous. And you are using your FPGA to control it.
That's fine because it'll still hit the switching point.
It's always writing, right? It's writing, not reading from it, right? So the FPGA, you are sending data to the LCD. You don't have to read it. You can still read from the registers to the LCD, but I don't know what kind of information do you need from LCD, right? Just a display module. You are writing to it to display something instead of reading something already displayed. We don't need to do that. We are writing something to it. So it's actually from the FPGA. The voltages are from the FPGA to the power supply, to the LCD, right? That means it's just one directional communication. So FPGA is not taking in any 5 volts logic as the input. So it's not going to be burned by the LCD's 5 volts. So that's going to be fine, right? So you just feel free to directly make the connections without having any step down voltage, intermediate levels or modules, voltage dividers or something. It's not required, okay? And for backlight plus and minus, you could definitely use the potential meter to adjust it. For example, you ground the backlight here, the minus pin, and the plus pin is the output of the potential meter. You can adjust it, which works actually. You can adjust the backlight to a certain level. But to make it simple, because I don't have that many potential meters, so I have to use the potential meter for the contrast pin as well. So then this guy will directly just connect it to the power supply and ground. So I think I did, so K to ground, and A to 3.0 volts. And that consumed a lot of power because that's a very bright LED. So I would just use the 3.0 volts from the power module, from the Aligo's power module, so I can confidently power it up. So you can see I put it here. So backlight minus to A. So A to 3.3 volts and K to ground. Okay. So now we are done with all the ports here. Okay, and then the enable pin is shorted to JB0. Okay, you can see JB0 is on the top right corner of the board. And RS pin is shorted to JB2. Contrast pin is shorted to the output of the potential meter. You know what that is, right? You know how to use it. So potential meter. Okay, so 5 volts on one terminal and 0 volts on the other terminal, and middle pin is the output. It's a voltage divider, right? So the middle pin is shorted to the contrast pin here. And you'll see how that works. So this is going to adjust the contrast, so it's not making the background too bright, and which dims your display. So you can adjust this guy to always make sure that you can clearly see the characters on the display. And then VCC 5 volts and ground zeros. That's it. So that's all the pins. Before we get into the logic, these are all the pins. So you do the hardware connection first, right? And then you'll start coding up your Verilog. So unfortunately, okay, so the code, both the sub module and the top, they are both provided by the textbook. Fortunately or unfortunately, you won't be able to get a chance to practice on coding it out from scratch, right? But it's provided, right? So you can definitely make it work very quickly. It could be a little bit boring, but it's gonna work. However, there's a additional task for you guys, but I'll talk about it after introducing the timing of this logic, with this diagram. So let's go back to the timing first. So now we understand all the hardware, the peripherals, the resources available, the pins and everything. Now we have the data sheet of the LCD module over here. The link, you can open it up. You'll never realize this is so complicated, right? So in Arduino, it's just one line, C code. So that's a digital circuit diagram, and this is a initialization procedure. Could be confusing, but let me give you an example here, right? So first, before you send the data to it, I think you can bring up your in-class probably. There are some questions relevant to the in-class question over here. Take a look. You all have your in-class number 6? Some of the LCD modules. Okay. So if I click this data sheet of the LCD module, you'll see the user's menu. I already identified a couple of typos over there, which is reasonable. This is not from the English-speaking country. Yeah, I saw a lot of other crazy typos from the toys I bought from Amazon for kids. Yeah, super simple mistakes, but. And coming down here, you can see the timing diagram, timing control, right? So for people program microcontrollers, they don't really have to look at the timing. But for a digital designer, FPGAs, ASIC, verification engineers, which are getting a little bit higher salary, right? You have to look at the bottom level timing diagram. Look at this one. Since we are not reading, right? We're not reading to it, reading from it. So disregard this one for now and only pay attention to this guy. Okay, so first the question for you guys is, if I'm saying this is a write operation, it's a write operation, okay? Which is writing to which?
Writing the LCD.
It's writing to the LCD, okay? It's not like, hey, I'm using the LCD, this is the LCD module, the write operation is the LCD writing to something else. That is wrong, okay? It's gonna be something write to the LCD, okay? Write to it. It's gonna be write to it or read from it. And wait, the question numbers are totally off. Do I could jump to number 5? I think I deleted a couple questions over there. So there are two registers. One is called an instruction register. Another one is called a data register. Okay, and the instruction register for short is called IR, and the data register for short is called DR. You can see from the tutorial, I have a really short description of it. Instruction registers or data registers. So you only have one set of data lines, right? How does it know like which register is writing to? So the instruction register is writing into instructions to configure the operating mode, the mode of the LCD. So for example, 2 lines of display, or clear everything after display, or have a blinking cursor, or just a solid cursor, things like that. Very minor things. Doesn't really matter that much, but you do have to initialize everything at the very beginning. So it's gonna be 4 bytes to be written to IR. It's gonna be 4 bytes, okay, 4 bytes to be written to IR in order to configure the operating mode of it. So there's a pin. If you look at all the pin resources available over here, if you are the person to design this whole system, right, and this is only a set of data pins, they share, it doesn't matter the instruction or the real data to be displayed, they all share the same data or the data bits, right? So if you want to notify the LCD module, hey, now I'm sending whatever showing up at the data ports, these are actual instructions, configuration instructions inside of data. You want to tell the LCD something, right? So that pin is the RS pin. RS pin over here. So when RS is 0, it's writing to the instruction pin, instruction register. So during the initialization process, you pull RS down, right? So LCD knows. So now the data displayed at the D0 to D7, these are actually instructions, not the data. I don't want to display them. Okay, these are configuration data. For read and write, so for writing to the LCD, this RW, this pin, need to be put down to ground. Okay? For reading, you need to put up to 1. Are we reading from it at all? Nope. So do you want to take a pin resource in my FPGA to toggle it? They're saying maybe at some point in the future I need to toggle it, right, to read from it. But for this, the scope of this lab, we'll never read anything from it. We shouldn't, because the 3.0 volts reading from 5 volts is going to damage everything. So we just put it down to ground. So we don't have to take a pin resource from the IPGA. Just put it down to ground. Just connect it to ground. Very simple, right? And let me see. Anything else I'm missing here? Contrast or also enable pin, so they're all done. Okay, yeah. And then next, after you have the RS, you can see RS here from the typing diagram. It doesn't show a 0 or 1, right? So it shows you a data bus. You know, you need to know how to understand this, right? For digital, usually digital should be either 1 or 0, but this is not. This is just something, right? So that means it's configurable. It could be 1 or it could be 0, that depending on the operation mode. It could be a write or it could be a read. So it definitely doesn't show you anything, right? But for write, it actually should be just simply being put down to ground, okay? Should be put down to ground. And for write, it should be shorted to ground as well. So this is always ground, so you don't have to worry about this one. So for enable, it's very interesting. You have to give a 1 to it at the very beginning, all right, and then put it down to ground. So actually the data won't be read or be written to the LCD until the falling edge of the enable pin shows up. And it has some requirements to make it very complicated. Okay? So first, the data has to be ready. Doesn't matter data or whatever. So the data has to be ready during the rising edge of the enable. And it doesn't really do anything to it, but it has to be ready. And then the falling edge, it definitely, whatever you want to send to it, has to be ready as well. So I think, this is a little bit confusing. I was thinking about why they want to separate it here. So I was reading from the manual. They are saying the address has to be ready here, and then the data has to be ready here. So address should be ready during the rising edge of the enable, and data should be ready during the falling edge of the enable. So that's why they separate it, because even so they are the same data set of data lines from DB0 to DB7. But the thing is, before this line here, before this time point, it's address, and after it is data. So the data, whatever being really written to the LCD is actually the data here, right? So the address is somewhere that it's gonna send the data to. That's a certain location you are sending the data to that address. However, I think this diagram is probably not exactly for this module. They just use a very general purpose timing diagram for multiple different display modules. Because for this one, we don't even have address. It's just directly data. There's no address. It's not like you have multiple registers. Every register has an address. You have to make the address available at the rising edge and then the data available at the falling edge. It's actually not true. So we don't even have address for this LCD module. So you can just ignore this little cross over here and then just treat the whole thing as one data, a piece of data. So just make the data available during the falling edge, and you will be fine. Okay, you'll be fine. So I coded up that way. I modified the code, and I didn't consider this cross over here at all, and it worked. So I think that's valid. Another reason I think this is a more general purpose timing diagram for probably different modules, the LCD display modules, is because you can see here it's just for writing operation. It's just writing, not reading at all. Why they still have to show the two options for RS. Oh yeah, that's probably, yeah, because they have to do R and DR. Sorry, never mind. Yeah, that's not the case. But only this one I think is probably for general purpose LCDs, not just for this one. See, we don't have addresses over here. Okay, so the requirements here, the bottom line is you need to pull down your RS first. Pull down your RS first, or put it up, depending on where you are writing the code to, right? Could be the instruction register, or could be the data register, or be the characters to be displayed, right? Doesn't matter. And then after a certain time period, you pull down the enable pin to write it into the LCD. So that's the most important sequence over here. Even though there are so many different things, you can just disregard it, because writing pin is always put down to ground. You don't have to worry about it. It's always 0, right? You don't have to worry about the timing here. It's always 0. And it's basically just the data has to be available over here, and you'll do the RS first, and then after a certain time period, you pull down enable in the middle of the data. Okay, so the data can be written into the LCD. So in that case, the data should be available before or after a certain amount of time. Before or after a certain amount of time of that falling edge. So here we introduce a super important concept for digital design, not just for FPGAs but also for VLSI design in the future. And when you are modifying the timing and play with the timing, it's all about setup time and hold time. Okay, if you make everything available super long before the rising edge or falling edge to trigger it, which could be always fine, right? You can always have the data available very long time ago. When the rising edge arrives, everything is ready, right? And even after the trigger, after everything is getting triggered, the data is still there. You can make it super long, like 1 second. But what's the problem? You are doing something at a very fast sequence, and the digital systems can run really fast, right? You want to leverage that advantage. So you just need a little bit amount of time right before the rising edge. So make the data available before the rising edge arrives, And after the rising edge, you just hold the data there for a little bit amount of time, okay, for everything to be latched into the memories. And then you're done. You just want to use the minimum instead of the longest, right? So during the next rising edge or falling edge, you can latch a different data. And the time right before the edge that triggers it is called the setup time. So you need the data to be set up over there for a certain amount of time and then trigger it. And also you need a certain amount of time after the trigger, the triggering edge, to hold the data there for a little bit, okay? And that's called a hold time. So the setup time and hold time. And you want to use the minimum instead of the longest. Does that make sense? So you need to make your data available before and after for a certain amount of time. And these times are called setup time, which is right before or after the triggering edge. Before, it's called the setup time. And after the triggering edge it's called a hold time, the hold time. All right? And I think we are, it's not actually number 7, but let's look at question number 7. The falling edge, the rising edge of the E pin writes instructions into the LCD module. Which one? Falling edge, right? It's the enable pin falling edge. Falling edge writes to it. So number 6, we're already talking about it. So RS 0 will write into the IR, 1 will write into the DR, RW 1 will be reading, 0 will be writing. So what's the minimum address setup and hold time?
Setup's 100 nanoseconds.
Mm-hmm. Hold time is 10 nanoseconds, right? The minimum. So you can see TAS and TAH. There's a TAS. Here's a TAH. They call it address, but it's actually data. It's a little bit confusing, but you can see the setup time here is before the rising edge. Because the rising edge, according to the theory over here, the rising edge actually places the address into it, and the falling edge enable write the data into it. So after the falling edge, you need to hold it for a certain amount of time. Okay. Another one, right? So disregard whatever the general purpose timing is. Okay. Just imagine that you are coding this up yourself. Okay, and you are writing to the instruction register. So RS should be put up or down. So you are writing to the instruction register. RS should be put down or put up. Down to 0. Okay, and then you need a certain amount of time, and then you put on enable so you can write the data into the LCD. So see here, for write, you put down RS, so you are right into the instruction register, and then you have to wait for a certain amount of time to put on your enable pin. So my question for you guys is, how long do you need to put that to wait until you put it down? Put enable pin down after the RS pin.
It's gotta be as long as the
TS
enable.
plus this, right?
Yeah.
So it means this plus this. So how much is it? So TS is 100. PWEH is 450. So the minimum amount of time you have to wait is going to be 550 nanoseconds. And that's not the answer for question number 9. Is question number 9 is that's just asking for the enable pulse width, right? It's the PWH, which is 450 actually. Yeah. But you just need to know that at least we need, when we are programming it, right? We need 550 nanoseconds to make it happen. So how do we implement it in FPGA? What are the resources available for us to make it exactly 550 nanoseconds or even longer? Probably we don't want to directly use 550. There could be some potential issues. That's a minimum, right? That's a minimum. What's the problem of waiting for longer? Like too long, it's wasting time, slowing down the whole system, right? If it's a bit longer, which would make sure that it satisfies the minimum amount of time, but also can guarantee that there won't be any errors. Just be safe. So if I let you guys calculate, right, how many counts, what the count max need to be to achieve 550 nanoseconds, how would you calculate it? How many counts, right? So you have a 100 megahertz clock, which is available. That's the reference, right? It's the timing reference. How to do the calculation? How? So it's going to be 100 counts per second, right? Rest of this. And we will need X amount of counts as a count max to achieve 550 nanoseconds. Right? X number of counts. And use X number of counts divided by this one. And this is cancel. And second, the time will be flipped to the top. So we're getting something seconds, right? And what is here?
550.
550. Right? Seconds. So just calculate back to find out X. Right? So what's the number over there? It's just basically this guy times this guy, right? Is it? Right? It's gonna be 550 times 100 times 10 to the 6th power times 10 to the minus 9th power. And that's gonna be minus 3. 55? Really? Only 55 counts. I think that's right. That's what we got. But we don't want to exactly just count for that much, right? We want to make it a little bit longer. Just pick up the numbers that you're comfortable with. I think anything larger than this will be fine. It could be even 10 times larger. I think it's fine as well. I think the code from the textbook used 1 millisecond. Like 2,000 times longer than that. So whenever you are seeing this guy, it's getting crazily stretched. It's not like this. Boom, boom, nope. It's like a boom, boom. According to the digital system, it's super slow. But according to us, it's pretty fast, right? But you get the point, right? I think we can try this number and even lower numbers and see what's going to happen for the LCD, see what kind of errors is going to show up to us. But I don't know, I haven't tried it yet. All right, so let's take a look at the code here really quick. Starting from the display module, top, I start from the top. They call it translator top. All right, this will make you sleepy, I'm pretty sure. I'm not getting the details. A lot of times you read it by yourself will be more helpful. But I went through everything multiple times already. So the concept is, let me show you this really quick first, so you know what will be expected over here. Alright. Power supply. So turn it on. And this is on. But the FPGA lost its data, I think. So here's a little potential meter, right, to adjust the brightness of it. You can see, oh, the contrast, I'm sorry, contrast. And you can see the dots, or the dots. And we don't have any data yet because the FPGA is not able to memorize anything. So I'm gonna open up the Vivado and program it. So for the configuration registers, you see, you look at the code, a piece of code like this. What it does is, it has 1, 2, 3, 4 steps. So these are all written into the IR, the instruction register, not the data yet. So it's called the initialization procedure. That's a step. You have to initialize everything. So first we write a 30 to it. So 30 comes from this guy. See? D7, 0, D7 to D0, it's going to be 0011. That's the higher nibble. And then the lower one, the lower nibble, has NF and don't care, right? So the don't cares, we just put a 0 in there. For N and F, you can find the information from the data sheet, right? So N does what and F does what. You can see from here. So for 3, where we got 3 is 0011, and 1 here you have 2 options, D or L. Okay, so D or L, it's just 2 options. It's a short name for it. You can see DL, right? So DL. So it's either 1 to 8 bits. Oh no, it's a 1 for the DL pin, DL bit. If it's a 1, it's gonna be 8 bits. If it's a 0, it's 4 bits. So which means if you put a 1 here, you are giving a 8-bit data to it. Otherwise, it's gonna be a 4-bit data. So definitely we are doing 8 bits. That's why we need a 1 here. So it forms a 0011, and that becomes 3, right, for this hex number. And for N here, so you can see for N, if it's 1, it's showing 2 lines. If it's 0, it's just 1 line. Okay? And from this result, you can see it's just 1 line, right? You don't see a second line. You see a second line? No. So it's 1 line. So for N should be what? 0, 1. 0. See? 1, 2 lines, 0, 1 line. For F, it's a 1, it's gonna be 5 times 10 dots. For 0, it's 5 times 7 dots. So the dots means it's a resolution of every little display unit. You can see every single one, a little rectangular shape. You can visualize, but if you have your own module, you'll be able to see it. It's being formed by 5 by 7 dots. So 35 dots in total to resolve a display the character. Okay, so this is a little matrix of dots, and it chooses to light up certain ones to display a character over there. You can't see it, but it can definitely modify the operating mode. It could be 5 times 10, could be 5 times 7. So we chose 5 times 7, and sometimes you'll see a 5 times 8. I didn't really count it, but I think it's probably, I don't know, I don't even care. It doesn't really matter. So some of the instructions are telling you it's 5 times 8. You don't have to count, right? It's just a one row of dots. It's missing or presenting, it, nobody cares. So we put a 0 here, then it shows a 5 times 7 or 5 times 8. That's the configuration of the display. And that's the first instruction you want to write into the instruction register. And then the second one, 0, 1, 0, 1, you can look at this one, okay? So 0, 1, you only start looking at D7. So 0, 1 clears, it clears the display. Which one is that? Is that one? 0, 1. It's this guy, right? 0, 1. So you do this instruction, it clears it up. So whatever display characters from the last experiment will be cleared. And 0, 6, they call it increment cursor. Increment cursor is incrementing cursor from left to right. You'll see the effect really quick. And 0F, it's a display on cursor blinking, so you'll see a cursor blinking all the time, which is not ideal, but you know, if someone likes it, you can definitely configure it the way that you want to just keep it off all the time. Okay, so where is the cursor thing? The cursor thing is over here, right? So the setup, you can read the menu to find out these bits, right? So eventually, if you have a 0F, which means all these are ones, right? 1F or 0F? 0F. 0F, okay? 0F. Why 0F? Shouldn't it be 1F?
It's the one above it.
This guy?
Yeah.
But the display on off, it's not the cursor. Right? We're talking about the cursor.
The entry.
Oh, this is display.
Yeah.
Display on cursor blinking. Wait. Oh, so this is the cursor control. Yeah, that's right. So this is cursor control. This is display control. That makes sense. Okay, so my quick question is, how does it know, like, which, the order of it? I'm just throwing a number to it. How does it know that I'm writing to that register to configure that mode instead of something else? Can I swap the order here? Can I swap it? It's a blocking assignment, so it's running one by one actually. But can I swap it? Can I change the order here? So, for example, okay, you have different instructions. These are just bytes. And you are writing it into different registers in order to control different modes, okay? So the thing is, you are just throwing bytes without giving an address. How does it know this byte is controlling, for example, display or cursor or clearing the display, but it's not something else? How? It is because the decoder. You see all the ones are being aligned at a diagonal here. So the one only shows up at a certain bit. So for example, I'm giving a 0, 1, it will never be something else. It's not possible. Because all the other ones shows up earlier. Does that make sense? So if you put a 1, like a 0, 1 like this, it will not be possible configuration for other entries. So it doesn't really matter because you'll see some examples, they change the order a little bit. And it doesn't matter. Okay, it's gonna work. All right. And now let's program it really quick. Then we'll let you guys do the quiz. Let you guys do the quiz. Here. I'll spend some time on Tuesday doing the lecture to wrap up this one. But this one will be a little bit challenging, just depending on the addition to the old lab, I think. I'll give you a quick demo and let you know what the added lab is, or added task is. Okay, so now it's showing a hello on it. Hello. And so you see the cursor is actually blinking. Cursor is moving, is blinking. And I could modify this one to control the contrast. Right? So this is definitely a better option. Right? So I have switches to control different data to be sent to it. So now it's at 0, so 0 by default is actually just hello, right? If I do switch it on to 1, the thing is my switch, switch 0 is not functioning really well because it's being abused. So I'm going to do number 2. So number 2 is showing for Lewis, right? And number 4 is showing college. And these are all programmed in the top module as the data being directly sent to the sub module. And so these are already given. So all the code, again, unfortunately, the textbook gave it to us, right? So your job will be simply get hardware connections, okay, and change the several operating mode really quick, and it should be a really simple lab. However, this year we're adding one more task to it. I'll probably give you guys more time on homework assignments, the due days. So what I'm trying to do is, remember the calculator we did last week or on Tuesday, last Tuesday. So I'm asking guys to merge the two modules, right? And you are using the display as a calculator's display. If I'm doing, for example, the two's complement calculator, right? You have 3-bit by 3-bit. If you put doesn't matter, depending on the number, right? It could be 1, 2, 3, 4. You start with unsigned numbers. You have a 3 plus 3. You have the numbers input from the switches. It should show up here. So it means 3 plus 3 equals 6. Okay, in addition to the display on these guys, okay, we want to show the exact operations of the calculator. If it's a minus, you have to show the minus. This is easier because you're just directly throwing characters to it. It'll be able to figure out the ASCII code and the byte and send it to this one. You don't have to, think about the signs and everything. It's just a character, right? Doesn't like this guy. You have to look at the lookup table and convert it to the corresponding patterns. But these ones are just the characters. Okay, depending on what characters you need to display on the module, you just throw it to it. So the ASCII code will be able to figure out which one to be displayed on the module. So we're actually making a real calculator. So input the data here and then display on the module. Okay, so we'll cover more about it. I'll think about it and give you some examples and templates on Tuesday. So make sure that everyone is having some fun, right? Can make it happen. All right, let's do the quiz. Work on the quiz.